we're going to add one more function to our list. We're going to graph the tangent function. Now, we do already know a handful of points, right? We know our special angles. We know that the tangent of 45 degrees, or pi over 4, is 1. We know the tangent of 30 degrees, or pi over 6, which would be right here. We know that's root 3 over 3, which you might not know off the top of your head what that is. Root 3 is about 1.7. So if we divide that by 3, it's somewhere between 0.5 and 0.6. So just estimating here. And we know the tangent of pi over 3, or 60 degrees, is root 3, so that's 1.7. So we know those. Great, it's a good start. We also know that in the fourth quadrant, tangent is negative. So if we think about the negative angles in the fourth quadrant, the tangent of them would be the negative version of the positive. So tangent of negative 45 degrees would be negative 1. Negative 30 degrees would be negative 0.5 or 6-ish. Negative 60 degrees would be negative root 3 or 1.7 or so. Okay, so we've got a bunch of points there. Can even connect them. Sorry, I forgot to mention we know the tangent of 0 is 0. Because it's the sine over cosine, so it's 0 over 1. But what about what happens after that? So in order to see that, we'll take a look at going back to our fun old right triangles. So here's a right triangle. It doesn't look like a right triangle yet because right now the acute angle is 0 degrees. But if I were to lift that up a little bit, you'd see that it's a triangle and the opposite leg is there. And as I grow, you can see what's happening to the angle. Angle A is getting bigger. I'll pause at about 10 degrees. And the tangent, which is the opposite over adjacent, has grown a little bit. I'll add that number to my list. If I keep going up, so I've got 10 degrees, let's stop at 30 degrees because we know this one. We know the tangent of 30 degrees is root 3 over 3, which, like I said, is somewhere between 0.5 and 0.6. We know the tangent of 45 degrees, so I'll move up to that one. Right now I'm just highlighting all the things that we know. But what I want you to see is as we're going from one to the other, so I'll do that again. As we go from 30 to 45, notice how the tangent is just continually growing. Okay, it keeps going, getting even bigger. Can we make it up to 60 degrees? Scroll up a little bit. Okay, well, so my other option is if I can't move B high enough, I can move A over, and that'll still make the angle A grow. So if I stop at 60, and there's my root 3. But here's the thing. Once I get past there, what happens? How big does this angle get? Sorry, how big does the tangent get? If I move A closer and closer and closer, so let's stop at 70 degrees, you can see, okay, so my tangent has continued to grow, which makes sense because now my adjacent leg, the denominator of tangent, is shrinking. At 80 degrees, it's even bigger. So our tangent gets pretty big. It's up at 4, 5, 6. How big can it get, though? 85 degrees. Notice how, I'm going to go back for just a minute so we can watch it grow. I'll actually add some rows to my table. About 70 degrees, 80 degrees, and you can see how the tangent, it's not just that it's growing pretty fast. 85 degrees. My tangent keeps doubling. 89 degrees. Well, look what's happened. Look at how big that's getting. Question is, how big can it get? 89.5 degrees. 89.6 degrees. It can get, now here's the problem is, I can't get infinitely close. But you can see that 89.9 degrees, you can see how big that tangent gets. So what's going to happen is, if we return this to our if we return to our graph here, as I get closer and closer to 90 degrees here, you can see that this is just going to go skyrocket up. But I can never quite get to 90 degrees. Go back to the sketch pad. If I try to move over one more time just to 90 degrees, I've got a problem here. It won't let me get to 90 degrees, and it certainly won't let me get to a tangent there, because since the adjacent becomes infinitely small, the fraction of the opposite over the adjacent becomes infinitely big. And so what we have here is similar to what we saw in our rational functions unit. We have a vertical asymptote right there. And because the graph, like I said, is reflected, it's negative on this side, we've got another vertical asymptote there. And so that's what tangent is going to do. It is going to go from a vertical asymptote, negative infinity, when x is negative 90 degrees, gonna pass through the origin. Notice how it does get a little bit flatter in the middle, and then start speeding up again, to another vertical asymptote at positive 90 degrees. So that was a total sort of wingspan or period of 180 degrees, or pi, and this is going to repeat itself every 180 degrees. So there'll be another one of those vertical asymptotes at 90 and at 270. So it'll just keep doing that over and over and over again. And that's the graph of tangent. I have one fully marked up here, so we can just assess it a little bit. The period is 90 degrees, sorry, is 180 degrees, or pi. The domain is not all real numbers like sine and cosine because of those restrictions, those vertical asymptotes. So what we'll say is that x cannot be, I'm sorry, this time I called it theta, so theta cannot be equal to 90 degrees, or any other number that's 180 degrees away from 90 degrees, because that asymptote repeats itself every 180 degrees. So I'll write 90 degrees plus 180 degrees times n, or pi over 2 plus pi n if we want to talk in radians. So that's what theta cannot be. So this is one of those times when we write a domain, instead of listing everything theta can be, we list everything it can't be. The range, you can see we have vertical asymptotes in both directions. So the range is all real numbers. And our vertical asymptotes we have at theta, or